Hello and welcome to Lecture 9 of Introduction to Computational Literary Analysis. Today we're going to look at pandas, a very cute animal and also a very common data science library for Python. And we're going to use it for some more word frequency analyses. So here we go. Okay, so I've fired up a new JupyterLab instance. I'm going to rename this something like, pandas, and I'm going to annotate that here too. All right, so pandas, besides being a very cute animal, is a data science library, and it comes with anacondas, so you should already have it installed. You won't have to install anything. And one of the common things that you tend to do in Python in data science is when you're using a library a whole lot, you don't want to have to type out the whole thing. So rather than type out pandas each time we want to use something from pandas, we give it a nickname. So we say import pandas as PD, which is the common nickname for pandas. So whenever you see PD, you just know it's just shorthand for pandas. So now we can type PD something, so like PD data frame instead of pandas.dataframe. It's just saves us a little bit of typing. Okay, so pandas handles tabular data, multi-dimensional data, which means that if you're dealing with complex data structures, it's often a lot easier to deal with in pandas because it's like working with a spreadsheet rather than working with like lists within dictionaries, within all kinds of other things. So the data structures that pandas has you use are usually like they're more than just these two, but there are two common data structures. One is a series, and this is for one-dimensional data, which is just, you can think of just as like a column in a spreadsheet maybe. And one that we're going to use a whole lot is called a data frame for two-dimensional data. So the dimensions it refers to, if you're imagining a spreadsheet, it just refers to the number of columns in the spreadsheet, to put it really, really simply. All right, so our goal here is to get a kind of spreadsheet where we have narrators. So all of our texts are like Betteridge, Clack, Bruff, and then Blake. And then, we have words underneath this. So maybe the word I appears 300 times. Maybe in Clack it appears 400 times. Maybe in Bruff it appears 800 times. I'm just totally making this up. And maybe in Blake it appears 1,500 times. Maybe you have other words down here, like him, and give it some arbitrary values. And so on. So we want to create a table like this. Yeah, I wonder if I can get this formatted nicely by doing something like this. Well, I'll fix that later. Yeah. So another way that we can think about this data structure is as if it were a dictionary of some sort. So we could express this same kind of thing as something that looks like this. So if we have Betteridge as our key in our dictionary, then we can have a dictionary inside that that has words like I, and this is 300, him, and this is 34, and so on. Okay, so that's Betteridge. And then we have another one called Clack, and this contains, I is 400, and him is 345. So, something that looks a little bit like this. So this is a dictionary that contains dictionaries. I can call it counts or something if I want. Okay, but we want to create something like this programmatically, right? So we want to create a program that does this for us, and then we will feed this into Pandas, which will sort of automagically create a data frame spreadsheet-like thing called a data frame that will allow us to manipulate it in lots of really useful ways. All right, so we're going to do everything that we have learned to do before, which is we're going to load in the text. We're going to chop it up according to narrator, and then we're going to do word counts on it. All right, so I might import a few other things here. I can say from collections import counter. This basically says get me the counter object from collections. I could have just typed import collections and then use collections.counter, but this is a little bit easier if I just only need that one counter. Okay, so I'm going to open again my readings, texts, content, Moonstone file. Read that, call it Moonstone. Now I'm going to refer back to an earlier notebook because I want to see where I've split this, because I've already sort of done the work of splitting this according to narrator. And it's somewhere down here. Yeah, okay, so here are the first few. So I'm just going to sort of copy and paste this. And I'm going to break it up according to... actually, yeah, I noticed in some of my other notes that I might be able to break it up by \n, which is a line break, and then these two, which might help me to ignore the chapters, but get just the narrators. So let me see how this works, actually. Uh-oh. Abort. All right. What's the first one of these look like? Okay, that's not very useful. Okay, that's the prologue. Okay, this is the first period. First period, first chapter. Yeah, what does 529 look like? Is that all a Betteridge? Okay, so what does the last 100 characters of that look like? What does the last 100 characters of the last part look like? All right, great. So yeah, this is the first period, so this is Betteridge. Clack is 31 to 39. Bruff is 40 to 43. And I think, let's see, what does 44 look like? Okay, so this is going to be Blake. Yeah, so all right, so I figured out, yeah, this is Betteridge. This is kind of a hack. So we can make another one of these called Moonstone Parts 2. And we can split this by \n, 2 pound signs and a space. And Moonstone Parts 2 will give us a different story. Third part, okay, so this is Clack. And let's just look at how this ends. Let's look at the last 100 characters. Okay, great. So that's Clack is 3, Bruff is 4, Franklin Blake is 5. Great. So I can just write Clack, Bruff, Blake equals Moonstone Parts 3 to 5. Yeah, that doesn't quite work. Yeah, so I can write a little list comprehension to do this. It's kind of needlessly complex. But yeah, let's just verify that this is Miss Clack. First 100 characters. Oh, no, that's not quite. Okay, there we go. Yeah, what about the last 100 characters? Great. Let's look at Bruff, make sure that what we're dealing with there is fine. Yep. Let's look at Blake. Great. Okay, so so now we have 4 characters, and yeah, and the strings of all of these narrators. Okay, so now we want to count these. So yeah, why don't we make a little function to do this? I'm going to call it clean text, and it's going to take text string, and it's going to return the cleaned text version of that. So first thing we want to do is lowercase it. Yeah, maybe we could have it return counted as well. So we can take that text string and lowercase it, call it lowered, and then because we've imported up here a counter from collections, we could say counter on that lowercase, but we first have to tokenize it. So let's say NLTK word tokenize the lowercase version of that. We want to count those tokens. Okay, so we're lowercasing it, we're word tokenizing it, and then we're putting it into a counter. Yeah, so for this to work, I have to import the NLTK up here. All right, yeah, let's give it a shot. It says list object has no attribute lower. Okay, so yeah, it looks like what's happening is it's telling us that it's trying to lowercase a list, but you can't lowercase a list. And that's because Betteridge is a list of chapters. So why don't I join this together with a \n. Yeah, because I forgot that this was a list of chapters. And then that should do the trick. Great. So now we have a list of all kinds of tokens, and we even have a list of some of the punctuation, which is going to be interesting because we're going to look at how some of these narrators use punctuation in a second. All right. Great. So we can produce that big dictionary, you know, something that looks like this basically, using this function. So yeah, we can, yeah, let's write this out kind of the long way. So Betteridge is counted version of Betteridge. Clack is counted version of Clack. Bruff is counted version of Bruff. And finally, Blake is counted Blake. So, you know, we would want to dry principle optimize this. So I could call this all counts. There would be a way to write this with a dictionary comprehension. But for our purposes right now, since there are just 4 of them, we can just keep it like this. So now we have this data structure. You know, it looks like this, where for each narrator you have a counter, and that counter is kind of like a dictionary, and it includes all of the counts for all of these characters. So now we have the kind of data structure that Pandas likes. Pandas likes things that are like dictionaries within dictionaries. So on the other hand, I don't know if it likes counters or not. So let's try and see whether we can pull this into a Pandas data frame. So to do that, we do pd.dataframe, which is just pandas.dataframe. And this dataframe object takes any kind of data structure that is 2-dimensional, and it kind of tries to shoehorn it all together into one data frame. So let's try that with all counts and just see what happens. Great. So Pandas is really smart, and Pandas just sort of figures out that if there's a word that doesn't appear at all in a certain narrative. So for example, if you look down here, Blake has one instance of was period. That's kind of unnerving. But that doesn't appear in anything else. So Pandas just says, well, it's NaN, so it's not a number. In other words, it leaves this blank just because it doesn't have that data. Yeah, so we can deal with this because really we do have that data, and the data is that this number is actually 0. So we should fix that, and yeah, maybe we should fix a few other things while we're at it. So if we see this dash, we want to do something with that. So why don't we just say that our text is actually, we're going to replace that dash. I wonder if I can just copy and paste this character, because it's difficult to type in dashes and m dashes. Why don't we replace that with that same character, but we're going to add a space on both sides so that the tokenizer does a better job. Yeah, and while we're at it, we could also replace all of these stars with just a space, because the stars are kind of throwing off our whole thing. So let's see how that works. Yeah, you still get this was thing, which is pretty weird. Okay, so how do we convert these NaNs to 0? Well, there is a nice function called fillNA, and we can provide it with a value. If we were to look at this, if I were to get my contextual help going on here, then it might tell us something about it, but yeah, it's not doing that at the moment. But fillNA, all it does is it takes all of the NaNs, the nada numbers, and it fills them in with some value. So if we run this, and here, let me make this a little bit bigger. Yeah, you can see all of the NaNs are now 0. So this is the state that we want this at, and I can call this something like narrators df. So df is a common shorthand in data science for data frame. So now that I have this narrators df, I can look at it, and it gives me this kind of view of it, where it says, here are the most, here's some of the first ones, right? And here are some of the last ones it sees. And you can see it's hiding a lot of other stuff here. So we could see much more of this if we were to, get the head, which is the first few rows, and we were to look at the first 40 rows maybe. So you can see these are the first words that we see in Betteridge's narrative, and the number of times they appear in all of the other narratives. So this is something interesting. So do we want to keep hyphenated words like that, or do we want to break them up into their individual components? Well, this is a decision that we'll have to make just based on the kinds of things that we're interested in counting. Yeah, these parentheses are pretty interesting. So it looks like Betteridge uses them 213 times, Clack 74, Ruff 31, Blake 62. And of course, the ending parentheses are all matched over here. Yeah, so what if we wanted to sort this so that we're seeing the most frequent words in all of them? Yeah, let's try this thing, sort values. The contextual help says it sorts by the values along either axis. So it tells us that we need to sort by something. So why don't we say by Betteridge? So it starts with the ones that Betteridge doesn't say at all, it looks like, and it ends with the ones that Betteridge says quite a lot. So he uses a comma 6,000 times. Yeah, and that varies pretty widely among the others. All right. Okay, so the next thing that we want to do is we want to adjust by the total number of words in each. So one of the things is, Betteridge is going to have a way higher count of anything just because he has way more words, right? So he has way more opportunities to use them. So what we want to do is divide each one of these columns by the total number of words that each of them uses, so that what we're dealing with is not word counts but word frequencies. Okay, so to do this we have to get word counts. So why don't we write a little function, call it number of words, and it takes a text string and it returns the number of words in that string. So we can tokenize it. Yeah, we can lowercase it. Really what we should do is we should just get this value out of counted, but I'm going to make this a separate function just for simplicity for the moment. Okay, so we have tokens, and I just want to return the length of that list of tokens, in other words, the number of tokens there. So I'm lowercasing it. I'm taking that lowercase version, tokenizing it, returning the link. So let's try out our number of words function. Great, yeah, so 94,000 words. Does that sound right? Okay, that does not sound right. Yeah, I guess this is tokens, so I guess it's counting a whole lot of other little things as well. Yeah, so I can get all of the word counts for all of these. Again, I'll sort of demonstrate the long way and the short way of doing it once more. So actually, we're already using that. So all numbers of words, we can make a new list of this. This is the long way of doing this. And then we could say for narrator, and we can give it a list. For all of these narrators, calculate the number of words for that narrator, and then add that or append that to our list that we're building up here. So this is the long way of doing it. And if we were to peek at this, how long is that? It's going to be 4 because we have 4 narrators. Let's just look at it. Oh, it says we have the same number. Oh yeah, because I'm saying bruff here instead of narrator. Great, yeah, so this is the number of words for each narrator. That totally makes sense. But a faster way of writing that, I'll show you the short way of writing it, is just to write a list comprehension. So I can do the same thing, but just say, it's kind of writing that for loop in reverse. So it's num words for that narrator in Betteridge, Clack, Bruff, Blake. So this is going to do the same thing. And if we were to look at this again, it gives us the same numbers. So this is just this thing here is just a shorter way of writing this. All right. So we have all of the numbers of words for Betteridge, Clack, Bruff, and Blake. And what Pandas allows us to do is something really neat. It allows us to divide these 4 columns by these 4 numbers. So let's see how that works. So narrators DF, we're going to divide that whole, this whole thing by all num words. Let's see what it did. Okay, so instead of Betteridge, actually, let me look at the original. Let me look at the original one for a second. All right, so originally here, for this pound sign, we have 24, 24, 9, and 30. And when we divide it by the total number of words, yeah, does this make sense? It looks like it's properly divided it by those 4 numbers. So it's divided all of Betteridge by the total number of Betteridge words there are. It's divided all of Clack by the total number of Clack words there are, and so on. Great. So now we have this thing, and we can call this like narrators frequencies data frame if we want. Okay, so now that we have these, we can do some interesting things where we can see how frequently certain narrators use certain phrases. So to do this, as an aside, I can write this down too. Pandas will allow you to get a column by indexing it just as if it were a dictionary. So, yeah, to get a column in Pandas, it looks something like this. And to get a row in Pandas, you use this loc short for location, and that will index a row. So here yeah, so let's try this. Let's get that word first. So yeah, it tells us that the word first appears with this frequency in Betteridge, this one in Clack, this one in Bruff, this one in Blake. So it appears the most frequently in Matthew Bruff's narrative. Yeah, what about the word diamond? Who says the word diamond the most? Okay, it looks like Betteridge, but only a little bit more than Bruff. Yeah, so one thing that is neat about Pandas is every Pandas data frame, it has this dot plot method, and it will tell us here, it just says makes a plot of a series or a data frame. So, yeah, we can plot. Yeah, we wouldn't want to plot the whole thing because it wouldn't know quite what to do with that much data, but if we have something like this, right, if we take a look at the type of this, it says that this is a series. In other words, it's like one-dimensional data. It only has one column. And this column here, with the names isn't really considered a column. It's considered the index or the labels of that. So I could plot this if I wanted to, and by default, it plots a line plot. So it's going to plot something that looks like this. So it's going to say Betteridge has the most uses of the word diamond, Clack much lower, Bruff much higher and Blake slightly lower. However, a line chart doesn't really make sense for this kind of data, because it implies that it's continuous in some way. It's not really continuous because we're dealing with 4 discrete values here. So we can change this to a bar plot just by writing kind equals bar. And there are a whole bunch of other plots that you can make as well. So yeah, this is more like it. Betteridge uses diamond this much, clack that much, bruff that much, and Blake uses it that much. So, we could even add words to this if we wanted to. We could say, instead of indexing it by just that word, we can index it with a list of words. So, how about moonstone? We can add it there as well. So now we have these 2 kind of like subplots that show us that Bruff uses moonstone way more than anyone else, but Betteridge and Bruff use diamond about equally as much. So, this is kind of interesting looking at this. Yeah, why don't we try this with something else, like punctuation marks. So here's an exclamation point and here's a question mark. And it looks like Miss Clack uses exclamation marks more than anyone else, which kind of makes sense for Miss Clack's, personality. And Franklin Blake uses question marks more than anyone else, which is kind of curious. Why don't we add a couple of more to these? So, yeah, what else? What other kinds of punctuation marks do we have? Period. That doesn't really tell us very much because they're so similar. Yeah, what about parentheses? Who uses parenthetical statements the most? Bruff does. That's kind of interesting. Okay, so we could do this all day if we wanted to, and just think of words and plug them in here and see who uses them more among these narrators. But it would be far more interesting to find this kind of thing computationally. So one thing, like a common practice in computational text analysis of any sort, is to find distinctive words. So distinctive words are words that are used in one category way more than in another category. So these categories can be anything. In this case, we're dealing with narrators. So what if we wanted to know what words are kind of characteristic of Miss Clack, for example? Like, what words does Miss Clack use, like this exclamation mark, that she uses way more than anyone else? Because this can kind of give us, like a glimpse into their character in a sense. So why don't we define this? We could say a distinctive word is used by one category way more than the average. Okay, so first we would need to calculate the average, right? So if we have this narrator's frequency data frame, capital F, Pandas has this neat function mean, which will just take the arithmetic mean or the average, of all of the values for the requested axis. So if we just run mean, you can see this gives us just the average frequency with which these narrators use all words, which is kind of not very useful, right? Because the axis that it uses by default is this columnar axis. So if we say axis equals 1, this tells us, no, actually we're interested in the mean of all of the words, not of all of the columns. So this is what we want. This is kind of the average use of the word first. That's the average frequency of the word the. So if we wanted to, we can even assign this to a new column, which will allow us to work with it better. We could say, we can call this the average. And now if we look at our data frame again, we'll see that it's added this new column average. So now this is useful because if we were to, let's look up exclamation mark. So the exclamation point is, way higher in Miss Clack, but what we're interested in is the difference between Miss Clack and the average, or any of these characters and the average. So we could do something if we wanted to, where we say, let's add a new column, and we'll define this as like clackness. As the frequency of a word in Miss Clack's narrative minus more than the average. Right? So if we have, I can write this in Python. If we have this table of frequencies for exclamation mark, we look at Miss Clack's value, and then we subtract the average. This is the what we're calling the clackness of exclamation mark. So we can compute the so-called clackness on everything if we want to. Just by in Pandas saying, okay, let's take this data frame and let's take all of the clack values, which is going to look like this, and we're going to subtract that data frame. It's average. So, Pandas understands that if you subtract two columns, what you really want to do is subtract every value from column A from column B. So we run this. This gives us a list of values where if it's negative, that means Miss Clack uses it way less than the average, and if it's positive, it means she uses it more than the average. So I can even assign this to a new column if I want to use it some more, and I can call it something like clackness, or I can just assign this to a variable on its own. And clackness now is going to be a Pandas series. And so we can do things to this series. We could say sort all of these values. And now what it's done is shown us the least Miss Clack word here, which is the. That's kind of unusual. I wouldn't have expected that. And the most Miss Clack word is the exclamation point. So the exclamation mark is actually the token that is the most like Miss Clack, the one that Miss Clack uses way more than the other narrators. So she is also one, which is kind of interesting. I think Miss Clack is really interested in her aunt, and she's interested in Rachel, so she uses female pronouns more than anyone else. And it does not surprise me that she uses Godfrey way more than anyone else, because Miss Clack kind of has this crush on Godfrey, Abel White. If we wanted to see more of these, we could do something like sort values, but we could say, don't show it to us ascending, show it to us descending. So now this starts with the most misclack token. And another thing that we could do is we could look at more of these by saying, show me the first 40 of these. So she's interested, Clack is interested in Rachel. She's interested in Godfrey Ablewhite. Obviously, she uses a lot of dashes. Yeah, of course she uses the word Christian more than anyone else, a lot more than anyone else. So that's in like her top 20 most distinctive words. Precious is pretty big, and the parts of her name are pretty big. So you can already see that we can almost hear Miss Clack if we look at her most frequent words, in a sense. So, we can abstract this into a function if we want, and say we want to get the distinctive words of a narrator. And we're going to want to feed it that data frame too. I mean, we could use the data frame that we've already defined. Yeah, but this can demonstrate taking in these two values for us. And, we could annotate this. It's probably a good idea. And this will get a series of the most distinctive words for a character. Actually, for a narrator. All right. So we need to get the average. And that's our data frame average. And then we get our narrator's frequency, and that's DF narrator. And then we define, distinctive as, again, our narrator minus the average. So this is our distinction. Okay, now we have a series. We want to sort the values of that series descending. Yeah, so I could say ascending equals false, and I can get the first 40 of them. First 40 most distinctive words for a narrator. So let's try this. Let's try it with Miss Clack because we already know what that is. Great. Yeah, so now we could try it with other characters too. So what does it look like with Matthew Bruff? Okay, so he's really interested in what the Indians are doing. So Indians and Indian come up a whole lot. He refers to Rachel as Miss Verinder instead of Rachel, of course, because he doesn't know her as well. He talks about Mr. Luker a lot, and he uses the word moonstone quite a lot. What does it mean that in is one of his frequent and distinctive words? What does it mean that of is one of his distinctive words? So, of as a really interesting semantic purpose, syntactic purpose. It kind of has this function where you can distance yourself with something by using of. So it's a word that can make anything seem a whole lot more formal. So there's an interesting argument that you can make just even using these very common words like of. His formality comes across in other words like Mr. Yeah, so what if, we could also make another version of this and call it least distinctive if we wanted to, and it would just do the same thing. Except for it would give us the least distinctive words. Really, we would not want to do this and just copy and paste a function, because we're repeating ourselves. So, another way of doing this is we could just return that distinction, and then we could sort it later. So this, by default, will give us like the least distinctive words. Well, by default, it won't sort it at all. So we could say, yeah, we could actually make this into more functions to make this easier for us. This will take distinctive series, and it will return that distinctive series, but we're going to sort the values, and we're going to get the first 40. Yeah, and so this is another version, but here we're going to look at the least distinctive. All right, so let's try this again. So most distinctive of distinctive words. Yeah, so this is bruff. And if we were to change this to least distinctive, now we get the least bruff. So the exclamation mark is the least Mr. Bruff thing we can find. Okay, so here's something interesting. These curly quotation marks, I'm just going to copy this into my clipboard here. Those are pretty interesting because they tell us how much dialogue happens in each one. So if I were to take my narrator frequency data frame, and if I were to look at just that beginning quotation mark, yeah, let's see how often it appears. Let's plot that as a bar chart. Yeah, so Franklin Blake has more dialogue than anyone else, it looks like. Or at least his dialogue is broken up into enough chunks. So this is something interesting. So, there are lots of things that you can do with this. You can say, you can extract words that are inside dialogue and words that are outside dialogue. And you could say what words are more common inside dialogue than outside it. You can do that for each narrator. Yeah, there are lots of fun things that you can do with that. In fact, a lot of these lesser distinctive words for bruff are kind of dialogue. So Bruff, Matthew Bruff and dialogue are not real friends. I could say, what are the most distinctive words of Betteridge? This should be fun. So Betteridge is really interested in Sergeant Cuff. Yeah, he really hates him, and so Sergeant comes up a lot here. A quotation mark comes up a whole lot. He's really interested in Rosanna Spear. He talks about Rosanna a whole lot. Here's Sergeant Cuff again. Of course, he talks about Penelope a lot. Great. What are the least distinctive words for Betteridge? I. That's really surprising. I wouldn't have imagined that. But I and me and my are the least distinctive for Betteridge. So Betteridge is very focused outside himself, it looks like. He's always thinking about what other people are doing and not so much talking about how he feels or what he did. In other words, he doesn't use the first person a whole lot. But yeah, he doesn't use the second person a whole lot either. So yeah, that is super interesting to me. Question marks also are not very distinctive. So yeah, I would encourage you to, while you're following along with all of this stuff, to try this out. Try looking at the most distinctive and the least distinctive words of everyone. Yeah, and try looking at some of these in particular. So, what if we were to look at how marriage occurs across these narrators, or Indian? That'll be pretty cool. So we can take our data frame again, and we can get the location for marriage. Who talks the most about marriage? And while we're at it, we can plot this as a bar chart. Brough. Matthew Brough is way more interested in marriage. Uses the word, at least, way more than anyone else. So I can copy and paste this down here and try some other word like Indian. Also, Brough uses Indian way more than anyone else. Okay, so you can already start to imagine that there are literary critical arguments that you can make about the narrators in the story using word frequencies. So we might not otherwise have a feeling that Matthew Brough uses the word Indian or is concerned with the Indians way more than anyone else. But this shows us very concretely that he uses this word much more than the average. Okay, yeah, so let's think about just one more thing. So right now we're dealing with tokens, but what if we were to mess around with using stems or lemmas instead? That would be kind of cool. So why don't we import the stemmer from the NLTK? So we could say, we've already imported the NLTK, but we could say from NLTK dot stem dot Lancaster import Lancaster stemmer. And now we can just say Lancaster stemmer somewhere. So why don't we come down here, and in our counted function we can replace this actually, so after we tokenize it but before we count it, we could say stems are Lancaster stemmer. Actually, I think we're going to have to instantiate that object somewhere. So we could say stemmer.stem. We want to stem each token. And so I'm going to write a little list comprehension that says stem each token for each token in my tokens. So this is again, you can think about this like a for loop in reverse. It's going to go through each of the tokens here. And it's going to stem it, and it's going to add it to this list that we're calling stems. So now I can change this to stems. Great. And why don't we run this? Where are we running counted? Because we have to do that again. Yeah, okay, so here we go. We're going to run this again. You can see that took a lot longer than before because the Lancaster stemmer is taking a really long time to do everything. We're going to fill in the NAs. And then, yeah, why don't we sort values by betterage? Okay, great. Now we've collapsed a little bit of the lexicon of this thing here. Yeah, so now we have a smaller vocabulary. We're only dealing with about 5,000 forms here. Run a few of these things again. All right, so now that we've done that, we can deal more with the stems rather than just the word forms themselves. So why don't we compare some words like some verbs? So how about think, feel, say, and exclaim. So hopefully our stemmer has taken words like, exclaimed and exclaiming and has collapsed them to exclaim. So let's see how this works, and while we're at it, we can plot it as a bar chart. Oh, right, because we're not looking for columns here, we're actually looking for rows. Okay, so think is way more a Bruff activity, something that happens way more in Mr. Bruff. Feel happens way more in Miss Clack. Say happens way more in Betteridge. And exclaim happens way more in Blake, although not by a whole lot. So, yeah, here we're looking at verbs after we stem it. Okay, why don't we copy and paste this. And yeah, we can try a few modal verbs. We can say might, could, would, can. So this would, this conditional happens way more in Bruff. Can happens way more in Blake. In fact, in Blake, all of the modals happen way more. So does this mean that Franklin Blake is more interested in the future, in potentialities? Does that build up the narrative tension? There are a lot of literary critical arguments that you could make based on the frequencies of these words. Might, could, would, can. Yeah, what is another one? May? Yeah, so apart from would, which is way more Matthew Bruff, yeah, Franklin Blake uses those a ton, So what I would want to do now is go back and look at how Franklin Blake uses these. You have to make sure that you really know the context the uses of some of these words and not just rely on their frequencies. So what I might do here, is look at Franklin Blake, which is stored in this variable. Maybe I can make this into an NLTK text object. I would first have to tokenize it, and then I could run concordance, on a word like might. Of course, I would want to make this repeatable in some way. So I could say this is the Blake text, and Blake text concordance for might. It normally comes after I might have done this, I might have got on, I might have suspected. So that's kind of Blake's idiom. What about can? We could look at can. So this tends to occur mostly within dialogue. I can or I can't. Can you eat and drink? Yeah, so is it just that words like can appear in Blake way more because we know Blake has way more dialogue? Is that it? So we would want to be careful with any kind of arguments that we make about the text based on these word frequencies. And the way to be really careful is to do concordances, to do searches, and to make sure that you know how these appear in context. Okay, that's it for today. Looking forward to talking to you more about this on Zulip.